In Lab 6 we will be pretending that the IKS01A3 expansion is a custom board with only one sensor, and we will generate the corresponding project. The application will collect the data from the sensor and it will print all measurements on the serial terminal. The sensor is the LSM6DSO inertial measurement unit. We will learn how to change the configuration of the sensor by increasing the output data rate. We will also increase the frequency of the main loop to read the data more often. This will reduce the overall latency. In this lab we will be configuring the sensor to take measurements as fast as possible. The sensor is typically configured to take 100 samples per second. This means that there are 10 milliseconds between consecutive samples. When the application is not synchronized with the data ready interrupt, the data read by the application can be stale. We need to increase the sampling rate as much as possible to guarantee that the data read by the application is fresh. We will configure the sensor to work at its highest output data rate, 6,666 samples per second. As in the previous lab, we will need to configure PB8 and PB9. PB8 and PB9 are the pins of the microcontroller that are connected to the I2C communication bus. This bus goes from the microcontroller to all sensors on the custom expansion board. Let's begin. Launch the STM32Cube IDE. Click on the File menu. Select New and then STM32 Project. The IDE may try to check if some update is available. If the network settings are not configured, the IDE will ask to configure them. You can safely cancel the operation as we have already downloaded everything we need. Wait for the IDE to load the list of microcontrollers and development boards. Then click on Board Selector. In the search field type L476. L476 is the part number of the microcontroller on the Nucleo board. A short list of matching boards will appear. Select the Nucleo L476 from the list. Click on the Nucleo L476 item to confirm, then click on Next. Type the name of the project and then click Finish. Accept the default initialization for all peripherals. At this point the Cube MX embedded in the Cube IDE may try again to check if some update is available. If the network settings are not configured, the IDE will ask to configure them. You can safely cancel the operation as we have already downloaded everything we need. Wait for the project to be generated. When you see the graphical representation of the microcontroller, you can zoom in with the mouse wheel. Look for PB8 and PB9 on the top edge of the microcontroller. PB8 and PB9 are the pins of the microcontroller that are connected to the I2C communication bus. This bus goes from the microcontroller to all sensors on the expansion board. Click on PB9 and select the I2C1 serial data line function. Click on PB8 and select the I2C1 serial clock line function. PB8 and PB9 are now connected to the internal I2C1 peripheral. The color of the pins is yellow-orange because the internal peripheral is not enabled yet. To enable the I2C peripheral, go to the left panel. Click on Connectivity. Then click on I2C1 to open the corresponding mode and configuration window. In the mode window, select I2C from the pull-down menu. Note that the color of the pins becomes green. The color becomes green because the internal peripheral to which they are connected is now enabled. Remember that we want to increase the frequency of the main loop to read the data more often. This means that there will be more traffic on the I2C communication bus. Then it is better to increase its speed. In the configuration window there is a tab dedicated to parameter settings. Go to the I2C speed mode item and select fast mode from the pull-down menu. The speed will quadruple, going from 100 kHz to 400 kHz. We are now ready to bring in the additional software from the XCubeMOOC package. Click on Additional Software near the top of the window. Click on the arrow corresponding to XCubeMOOC. Unlike previous labs, we need to bring in 3 different pieces of code. First, we need to bring in the low-level driver for the sensor on the custom expansion board. Click on the arrow corresponding to board component. Go to the LSM6DSO item and select I2C from the pull-down menu. Second, we need to bring in the middle-level board support package. Close the long list of components and go to the board support item. Click the checkbox for custom motion sensors. Third, we need to bring in the high-level application code. Click on Device Application. Applications can be found in the pull-down menu. To be able to see the full name of the application, you may need to adjust the width of the columns. Scroll down to select the Data Log Terminal application. You may notice that applications written for the IKS01A3 expansion board are grayed out and cannot be selected. The Data Log Terminal application is written for a generic custom expansion board. Finally, click OK and you are back to the main window. We have brought in the drivers, the board support package, and the application code, but we need to enable them. Go to the left panel. Scroll down. Click on Additional Software. Then click on STMicroelectronics XCube MOOC to open the corresponding mode and configuration window. In the mode window, click the checkbox to enable the component drivers, the board support package, and the application code. In the configuration window, we must select from the pull-down menus the pins that the application must use. First, we need to specify the input communication bus, I2C1. Then the pin associated with the user button on the Nucleo board, PC13. We need to specify the output serial peripheral, asynchronous UART number 2. Finally, the pin associated with the green LED on the Nucleo board, PA5. Remember that we want to change the configuration of the sensor by increasing the output data rate. In the configuration window, there is a tab dedicated to parameter settings. Change the output data rate of the accelerometer by selecting 6666 Hz from the corresponding pull-down menu. Change the output data rate of the gyroscope by selecting 6666 Hz from the corresponding pull-down menu. You can also change the full scale of each sensor in LSM6DSO. By default, the accelerometer sensitivity is set for 2G full scale, while the gyroscope sensitivity is set for a 2000 degrees per second full scale. We can now save the project, which will trigger the actual generation of the code. The code is now generated. Expand the core folder. Then expand the source subfolder. Double-click on main.c. You will see the generated code. User code can be added between sections marked as user begin and user end. User code added inside these sections will be kept when the project is regenerated, while user code added outside these sections will be lost. Remember that we want to increase the frequency of the main loop to read the data more often. Expand the MOOCs folder. Then expand the app folder. Double-click on app xcube MOOCs1.c. You will see the source code of the application. First, we will modify an internal variable to make the output less verbose. Go to line 50 and change the initialization value for the verbose static variable from 1 to 0. This will cause the application to just print the raw numeric values of the measurements on the serial terminal, and nothing else. Second, we will modify the delay so that the main loop runs more frequently. Go to line 203 and change the delay from 1000 milliseconds to 50 milliseconds. This will cause the loop to run 20 times a second. Save the modification. We can now build the project and create the binary. No other project should be open while we build this project. The focus should be on the main.c window. Click on the hammer icon on the top. In the console, you can verify and monitor the compilation process. The compilation should be completed with no warnings or errors. Now it is the time to connect the Nucleo board with its expansion to your computer by plugging the USB cable. When the board is connected, we can flash and debug our application. Click on the bug icon on the top, then click OK on the pop-up window. The firmware binary is programmed into the target microcontroller and run. The debugger will halt the execution at the first breakpoint, that is at the beginning of the main function. Click the play button to go past the breakpoint and let the firmware run. Now the firmware is running. Let's check the output. Minimize the Cube IDE window and launch the serial terminal emulator, term. Remember to connect to the serial port associated with the Nucleo board. Remember to set up the serial port so that it works at 115,200 bits per second, 8 bits, no parity, 1 stop bit, no flow control. As soon as the serial terminal emulator is connected to the serial port of the Nucleo board, you should see a fast flow of data. You can shake or change the orientation of the board and check the output of the accelerometer. You can rotate the board and check the output of the gyroscope. When you are done, go back to the IDE and click on the Stop button to stop debugging. We can now close the project. Right-click on the project name and select Close. Thank you.